And welcome again. As you can see, we have set up some kind of experimental setup to measure the voltage, and the statement itself reads that to measure DC voltage, a parallel plate capacitor is used in the layout as shown in the diagram. One plate of the capacitor is fixed while the other can move perpendicular to the plane of the plates with the necessary insulation provided, of course. A spring with a spring constant K equals 177 Newton per meter is attached to the fixed plate. Okay, fixed plate. This plate is fixed to what? I think there should be to movable plate. Instead of writing the fixed plate, we can write here the movable plate, because this plate is movable and this plate is fixed and capacitor is connected to the movable plate. So find the potential voltage measurement based on the changes in the distance between plates. So it's a good question, and we know that due to the charge distribution, the capacitor plates attract each other regardless of polarity of the voltage applied to them. And in equilibrium, because I am not going to shift my focus towards voltage distribution and polarity of the plates, and it doesn't matter as well, because I know that in equilibrium the spring force is equal in magnitude to this attractive force. The force will be attractive in any case, and but in the opposite direction. So we can write this equation of equilibrium as we know that this electrostatic force is going to be equal to q square divided by 2a epsilon naught. You can place one field in the electric field of another and find the force by writing F equals QE, and it comes out this, and then you can write Q equals C, potential difference, CB, CU in this case, and since C is equal to epsilon naught A by D, so you will get this result eventually as 1 by 2 epsilon naught A U square by D square, and this is the force in equilibrium. And if the separation between the plates has been changed from D naught to D, then the spring force that is Kx, because the change in a spring must have been D naught minus D, because the distance between plates has been changed from D naught to D, so that length of a spring that is being compressed is D naught minus D, and this must be equal to this electrostatic force, half epsilon naught A U square by D square, and from here you can find the value of potential difference as simply as 2k epsilon naught A D under root D naught minus D, and since D naught minus D is the compression in the spring, call it X, and you can write this expression as U equals 2k by epsilon naught A D. You can write D as D naught minus X and D minus D naught as X. So the next result is going to be root X, and this is the solution, I think. Potential energy in terms of X. If you wish, you can draw it, and I think the problem is solved. So thank you for watching.